Hello everyone. So today we'll be solving a LeetCode hard problem, a maximum element sum of a complete subset of indices. So we are given and one indexed array nums, and our task is to select a complete subset from nums. And what is a complete subset? Where every pair of selected indices multiplied is a perfect square. So for example, if we select like two elements ai and aj, then the index corresponding to those elements I and j should be a perfect square. So for example, we need to select those indices I and j such that I into j is perfect square. And now out of all possible ways of choosing these complete subsets, we need to return the sum of the set which has the maximum sum, and this sum would be corresponding to the values present at that particular indices. So for example, in this given example, since the array is one index, we'll mention is 1, 2, 3, 4, 5, 6, 7, 8. Now we need to choose indices such that their product is a perfect square. For example, if we choose 4 only, so since 4 is a perfect square, so the result can be 5. The value corresponding to 4 is 5. So for example, if we choose 8 only, then the value corresponding to that would be 9. Alright. Now suppose we choose 2 and 8. Right. So since 2 into 8 is 16, which is a perfect square, hence value is 7 plus 9, and values corresponding to them are 7 plus 9, which is also 16 only. And hence this is the maximum sum that we can get out of all possible ways of choosing a subsets. So like we can choose 1 and 4 also, 1 and 4, since this is a perfect square. So here the sum would be 8 plus 5, 8 plus 5 equals to 30, and so on. So here the maximum sum that we can get is 16. Now going on with another input, for example, if we see here 6, 7, 8, 9. Now if we choose as we can see, like this element is 10. So what if we choose again we choose 2 and 8. So 2 into 8 is 16, and elements are 10 plus 9, so which is 90. But we see the output is 20, so we need to find out another configuration. So what if we choose 1 into 1 into 4 into 9, because 4 into 9 is 36, which is also a perfect square. If you multiply it with 1, then 1 into 9 is also a perfect square, and 1 into 4 is also a perfect square. Now values corresponding to these are 8 plus 8 plus 4, that means 20. Hence the maximum sum that we can get here is 20. So now let's see how means how a number becomes a perfect square. So we'll see the prime factorization of any given any number and see how means what is the difference of the prime factorization between a perfect square number and a not perfect square number. So for example, suppose an integer n can be expressed as a product of prime factors, which is p1 ki power a1, p2 ki power a2, where p1, p2 and these are prime factors, and a1, a2, ak are the power of those primes. So for n to be perfect square, all of these powers should be even, right? For example, if we have 36, then its prime factorization is 2 square into 3 square. So as you can see, the power of 2 here is even, as well as the power of 3 here is also even. That's why this number is a perfect square. Hence, all exponents of the primes must be even numbers for a number to become perfect square. Now we need to find two numbers such that their product becomes a perfect square. So we need to find out two numbers I and j such that their product is a perfect square. So what if suppose a number is not a perfect square, I is not a perfect square, then what would the prime factorization would look like? We have suppose p1 ki power a1, p2 ki power a2, p3 ki power a3, and so on, pk ki power ak. Now this means sum of those a1, a2, ak's would be odd, like sum of the A1, A2 or AK would be odd, right? For example, suppose we have the number as 72, right? 36 into 2. So here the prime factorization will be 2 to the power 3 into 3 to the power 2, right? So if we segregate this number, means remove, separate the square powers alone. So we can 2 square, 3 square, and then the odd power can be separated like this, right? So we can see this number is a perfect square, and now this is being multiplied with a prime number which has a or means which has a odd power, right? So we'll try to since we need to make the product as a prime, as a perfect square, what if we segregate the part which is making it a perfect square and only deal with the part which is means not making it a perfect square, right? So this is what we'll do. We'll strip away the square parts of any number to find its core. So for example, n would be s square into k. So for example, if it was 72, then it would be 36 into 2, which is 6 square into 2. So here s is 6 and k is 2. So we need to find this core of k, which is not means which is disturbing the perfect square condition for any number, right? Now once we have these cores of I and j, we need to multiply these numbers together to make it a perfect square, right? So suppose we need to find out two numbers I and j such that they satisfy the condition like I into j are perfect square. So if I was x square into core of I, we are means writing I in the form of this, and similarly if j was y square into core of j, then I into j would be x square into y square. So this part is a perfect square. Now we need to make this part as a perfect square so that the entire product of I into j becomes a product, becomes a perfect square. Now core I into core j, we need to make this a perfect square, and we know this was the prime factorization. So these values, and since we have already separated the square part, so these will be odd part, means odd exponents of primes. And hence if we want to make the product of two numbers who have odd exponent of prime, then these two numbers must be equals to each other, right? For example, if we have 2 ki power 1 and 3 ki power 1, so we will never be able to make this product as a perfect square, right? If we have the means prime factorization of a particular number as product of primes with odd exponents, then the second number should have the same configuration so that this means adds up to become an even number. This also gets add up to become an even number, right? So that the overall number becomes a perfect square. Hence we derived the core of both these numbers that we are multiplying should be same. Okay, so this is what we have till now. We segregated the perfect square part from each number, and then we means reduced to the condition that the core part of two numbers should be same for them, for their product to become a perfect square. So let's now see the brute force approach that we can go through, since n is of the order of 1e4 here. So we can fix the first number, we can try, iterate through every index I and try to pair it with every other index j, and if they form a perfect square, we group them together. So for example, if we are at a particular index I, we will group it with all j1, j2, j3 and so on, such that I into j1, I into j2 and so on, these are perfect squares. If these are perfect squares, then we can put them in a single group and simply find out the sum. Also we can know if a into b is a perfect square and b into c is a perfect square, then a into c will also be a perfect square. Hence, these two values will also reside in the same group, because we need to like find subsets such that all pairs, means the product of all every pair of selected indices must be a perfect square. Alright, not only adjacent ones. So this is what we will follow. We will fix the I. So let's see the code here. So we'll iterate through I from 1 to n. Now we have created this visited so that we do not like once we have for 1 we have got 4, 9, etc. Then for 4 again we do not, means find out this 9 and then suppose 16 and so on, so that number of iterations are less. That's why we have created visited. If it is already visited, then we just skip the loop, or the current group sum is nums of I minus 1, because the indexes are 1 based. So here means the normal vector is only given, so we are assuming like the indexes are 1 based, but values are residing in 0, 1, 2, these indices only. All right. I hope you are not confused from the statement. If it is given as one indexed array, that only means like for these ij's we need to account them as one based indexing, right? That does not mean like the vector would start from nums of 1. I hope like there's no confusion regarding that. Okay, so then we'll check for all possible pairs of j. Now we'll find out the product and the square root, and if it is a perfect square, like root into root is same as the product, that means this product is a perfect square, and hence we'll increase our current sum by j minus 1 again, because one based indexing was there, and we'll update the max sum and uh, finally return it. So since like n is of the order of 1e4, so this iteration would be of the order of n square, we will say, but it will not run n square times because of this condition of skipping, because since we are going it from for 1, all those values of 4, 9, 16 would be skipped, right? These values will never be executed. From 2 means 8 and 32, these values would be skipped, right? But in the worst case, like suppose it will take n square, so it would be of the order of 1e8. And let's try to see like if this gets accepted in uh, on LeetCode platform. So let's try to submit it. Yeah, so as we can see, like it gets accepted, but the runtime is very huge, all right, and it beats none of the solutions. So hence like this approach works, but we need to like find an algorithm of the order of like something of n root n or n log n approach, so that like even if an interviewer asks us to optimize this approach, we can be able to. So the optimal approach would be to like means since we are doing prime factorization of each number, what if we were able to like find out all the prime factors of a particular number and then identify those which has a odd power, because we are seeing like only those, means only those primes which has like odd power disturbs us, disturbs the perfect square condition, right? So what if we like find out those prime factors? Hence, to find out those prime factors, we will be needing to find out the prime factorization of a particular number. And for finding out the prime factorization of a particular number in the most optimal way, we have the sieve algorithm. So I hope like you are aware of sieve. I will be using sieve to solve this problem. Sieve, what sieve does is it will be means allowing us to find like find prime factorization of a number x in big of log x complexity, right? So what we do here, like instead of sieve, if we try to like find out all the devices in root n, then the complexity would be n root n, and again like the solution would not be the most optimal one. Hence I am like using sieve here, so that we can find out all the optimizations and means find out all the factors in um, log n, and hence the overall complexity would be of the order of n log n. So how sieve works, I will not be explaining that here. You can like see, go and see CP algorithms website, and there means it is explained in a very well manner. So this is the code of sieve. If you want to like find out means what sieve here is does is here SPF stands for, I will explain it a bit so that if you are not aware of it. So SPF is smallest prime factor. So what we are trying to do is we are storing the smallest prime factor of each number. So small stores the smallest prime that divides it, right? So if SPF of x is x, then x is prime. For example, 2, 3, 5, 9, 5, 7, 11. The small means the smallest prime number that divides these numbers are the number itself only, right? So if SPF of x is the same as x, then that number is prime. Else the number x is composite. So if for any number, for example, if we have like 18, so if we know the SPF of 18, so what will be the SPF of 18? It will be 2, right? So we can make 18 by 2. Now we get 9. Now if you have already stored this SPF of 9, what will be the SPF of 9? It will be 3. So we can make it 3. Like again we will find the SPF of 3, which is 3 only. Hence we will make 3 by 3 equals to 1. So as we can see, we divided it by 2, 3 and 3. So the prime factorization of 18 is 2 to the power 1 and 3 square. So this is how like we find out the prime factorization of a particular number using this smallest prime factor array. So this is the sieve algorithm where which runs in n log of log n. This complexity comes due to the prime harmonic series that happens due to this I into I, and we are increasing it by I steps. I like would means if you are not already aware of sieve, I will like tell you to please go watch a tutorial on it or read about it online, then you will be like getting it. Or means this is the code, so like you can go through it as well and maybe you will be able to understand. So once we have the sieve algorithm, will be for each index x from 1 to n, we'll find out its prime factorization, right? And why we are finding out the prime factorization? So that since each number we are representing n as s square into k, where this was the perfect square part and this was the core part which had like odd exponents of prime, right? So since this had the odd exponents of prime, we are trying to find out that essentially if a prime factor appears an odd number of times, it will stay in the core, and if it appears an even number of times, then it is removed or it is a part of this s square. Alright, so we will be finding power of each prime in x, where x ranges from 1 to n. So initially the product is 1. Now we'll be using the means SPF array to find out the prime factorization of x. So initially this p stores the smallest prime factor that divides x. So while p is dividing x, we'll be increasing the count. So if we were p was 2 and suppose it was 36, so 36 by 2 then becomes 18, then 18 by 2 again, so it becomes 9. Hence this count would be 2 for 2. Alright, so after dividing 36 by 2 square, we get 9. So hence we'll be able to find out the power of 2 in 36 using this SPF. Now if the count variable is odd, then only it would be part of the core of that particular number. Hence will be, if the count variable is odd, then we will be multiplying p with the core part. Alright, and then again we'll execute this loop till means 9 will become 3, 9 by 3 equals to 3, and 3 by 3 equals to 1. So as soon as it becomes 1, we'll be exiting this loop. So this loop is to like find the power of each prime in x, and this will be means of the order of log x complexity. Alright, Now once we have these, means once we have the prime factorization of each number and identified the code parts, then like we can group these core parts together. So for example, if we have multiple values like a1, which has like suppose s1 square into k1, and a2 which has s2 square into k3 k2, and so on. So if you want to like make this multiplication as a perfect square, then since this part is already a perfect square, we need to make k1 into k2 a perfect square. And we already seen above that this k1 should be equals to k2, right? So since we like need to, means this a1 should be s1 square into k1, s1 square into k, and a2 should also be s2 square into k, right? So if we have just identified this unique core part, then the number of values which has this k as the core part, these all values would be of same group, right? Same subset. So to identify the elements which belongs to a particular core part, we'll be creating a hash map which will be mapping the core values to the sum of those elements. So for example, here indexes a1 and a2 had a core part as k. So we'll be like mapping k as, means m odd prod. Odd prod is the name of map. So odd prod of k would be like nums of a1 plus nums of a2. Okay, and so on. All those values which has the k as core part will be taking the sum of all the elements on there. So if the prod, means this product variable that we had was 1, that means the core part means the n is a perfect square, right? Because there was no values which had, means there was no prime which had a odd exponent. Alright, so hence the index itself is a perfect square. Example 1, 4, 9, 16. Here the core square part is 2 square, but the k is 1 only, right? So hence if prod is remains 1, their core is 1. So all such indices we can, means pair them together. Because since they are already perfect squares, we can form a pair with each other only. And if prod is greater than 1, then that means like these are indices which have core value greater than 1. So we'll be adding nums of I to odd prod of prod, where odd prod of prod, it's mapping the core value to sum of elements. And finally, we'll be taking the maximum of the sum of perfect square indices, like this case where prod is 1. So we'll be grouping all the values at the perfect square case and taking maximum of for all k in odd prod map. So hence like we using this approach, we'll be able to like find out the solution in n log n complexity. Alright. So this will be the overall code. We are creating this odd prod map to map the core component of each number to the sum of elements. We are creating this maxi variable. Now we'll be moving from means I equals to 1 to I equals to n for each x, and then we'll be calculating the power of each prime in x as we have seen above. And now if prod value is not equals to 1, means prod is greater than 1, then we will be increasing the map of prod with the nums of I. And else this is the case of like 1, 4, 9, 16, the perfect square condition. So we can simply pair them together. So we'll be increasing this maxi variable that we created initially, which had a value of 0, will be means for all these indices will be increasing its sum, so that in the end maxi already has, means sum of perfect square indices values. And hence in the end we'll just iterate through the odd prod map and take the maximum for each k, for all k, for all cores possible, and finally be returning the maximum. So this would be like, since as you can see, we this prime is taking in log x, and since this can go up to maximum to n, so hence log of n, and this external loop is of the means running untimed, so the overall complexity is n log n. And the brute force approach had a complexity of big of n square, where we are looking for all possible pairs for each I. So let's try to like submit the code here. Let's try to look the overall code. So we just created the means find out the SPF for each value, and we calculated for each core. So let's try to submit this on VS Code and see, like initially it beated 5% of the runner, and now it beats, like it runs in 35 ms, so it beats most of the runtime. So like I hope like you now have understanding of the CEV algorithm, and uh, uh, will be able to use it to identify the prime factorization of each number in log of x. And yeah, if you have any doubts, feel free to comment down. I will be happy to respond. Thank you for watching.